Hi, I'm Leon, and today I'm going to explain deep Q learning. First off, what is deep Q learning? Well, it's an algorithm that teaches the computer how to act in a complex environment. I'm going to demonstrate this by teaching the computer to play the game Pong. Pong is a game where you control a little paddle on the right, and there's an opponent paddle on the left. Like table tennis, you want to hit the ball past your opponent to score a point. But if the opponent hits the ball past you, then it gains a point. Now, the opponent is a simple algorithm that starts off playing very slow and tries to follow the ball. But each time you score, the difficulty increases, and the opponent will not only move faster, but start predicting the path of the ball. So at 100% difficulty, the moment you hit the ball, the opponent will predict its path and move to the final location. That means for our deep Q learning algorithm to beat it, not only would it need to predict the path of the ball, but it would also need to hit the ball away from the opponent and anticipate its actions to outplay it. Our deep Q learning algorithm, which we'll call our agent, will control the right paddle on the screen. It'll start off much faster than the opponent on the left, making it easier to learn the basics. But as it approaches 100% difficulty, the playing field will level out and the agent must beat the opponent with skill alone. Before we take a look at how the deep Q learning algorithm works, let's analyze some of the components that dictate how humans learn. First, we have our memory. When we do something, we store it in our memory to replay and learn from in the future. In addition, we have the decision-making processes in the brain. This is what allows us to say, given my knowledge, I think this is the best action to take. In our algorithm, we're going to simulate this using something called a neural network. Now, neural networks are a rather complex concept, so I don't have the time to fully explain it. But you can think of it as a model of the human brain. It has neurons and synapses being the connections between the neurons. So when we give it some data as input, it figures out how to get to a specified output, converting the input to an output like a function. In our case, the input would be the screen and the output would be the best action. The issue is, we don't know what the best action is, so we can't train the neural network directly, and that's where deep Q learning comes in. It provides a method of predicting what the best action is, so we can train our neural network. There's one last thing we need to do before we can implement our deep Q learning algorithm. We need to define a reward function. You see, when humans learn, we set goals, and whenever we get closer to achieving them, we get happy, and whenever we get further away, we get sad. This happiness and sadness can be thought of as positive and negative rewards, and our brain tries to maximize our rewards. Our agent will operate on the same principle. The only issue is it doesn't have goals. Instead, we're going to look at the environment to determine whether or not it's doing well. If the agent does something we like, we give it a positive reward, and if it does something we don't like, we give it a negative reward. The function that calculates the agent's reward is called the reward function. In our game, there are two situations we need to consider when making our reward function. First, if the ball is heading towards us, we need to calculate the path of the ball and reward the agent if it moves towards the final location of the ball. However, if the ball is moving away from the agent, we'll just give it a bunch of free rewards. This incentivizes the agent to hit it past the opponent, because if the opponent hits the ball back, it'll get fewer points, while the ball is moving in the agent's direction. Now that you understand the basis for all the components of a deep Q learning agent, we can get into implementation. Like we discussed, the first thing we're going to need is some memory. Our memory will be just one giant array that stores the last 1 million frames of the game to learn from. Actually, hold on. One minor modification here. Instead of learning from each frame itself, we're actually going to feed in some data about the game. Namely, the opponent's paddle position, the agent's paddle position, the ball's position, and the ball's direction. Because there's so many pixels on the screen, it takes the agent a while to learn. So feeding it some basic info about each frame, instead of the frame itself, allows the agent to learn much more quickly. Now that we have our memory, we can create our neural network. The neural network will take the game data we just spoke about as input, and will return 3 values as its output: the predicted reward for going up, the predicted reward for going down, and the predicted reward for doing nothing. Then, to select an action, all we have to do is select the largest of the 3 rewards. So if it gave us the estimates of a reward of 1 for going up, 5 for doing nothing, and 10 for going down, we would choose to go down because it has the highest estimated rewards. After we select an action, we perform the selected action and save the following to our agent's memory: the frame, the action we took, whether or not the action resulted in the game ending, and finally, the reward obtained from the reward function. I want to make it clear that although the reward function rewards the agent for its action in that particular frame, the agent isn't just predicting the reward for that frame. It's predicting the reward in the long term, which is what makes it difficult. For example, if the agent hit the ball towards the opponent, it wouldn't lose any rewards the very next frame. But 50 frames later, when the opponent hits the ball back, it'll be missing out on rewards that it would have received if it had hit the ball away from the opponent. So, when the neural network predicts the rewards, it needs to learn how to account for these long-term rewards to make better decisions. Now that I've made that clear, all that's left is training the agent on past memories. You see, the agent operates by estimating what the rewards are for each action. Before training, these estimates are as good as random guesses. So training the agent entails that we teach the neural network to create more accurate estimates of the reward for each action. Doing this requires the Bellman equation, which states the following: a better estimate of the reward for the current state is the reward we received for the action we took, plus the maximum estimated reward of all the actions for the next state times a discount factor, which dictates how far the agent should look into the future when making its reward estimate. In a bit more detail, the maximum estimated reward for the next state means that we take the frame after we've made our action and have a copy of our neural network, make an estimate for the reward of each action, and take the largest of the estimated rewards. This value is then multiplied by what is called the discount factor. A discount factor of 1 means that the reward a million frames later is just as important as the reward now, and a discount factor of 0 means that we only care about the reward for that frame. Long-term rewards don't matter. In practice, we use a discount factor of 0.99 because we want to maximize rewards in the long term, but using a discount factor of 1 would have the agent trying to predict rewards 10 hits down the line, which is literally impossible. Additionally, we don't use the Bellman equation on the last frame of the game. Since there's no more opportunity for future rewards, we just feed it the reward it received for that specific frame. The last thing to note is that the Bellman equation uses a copy of our neural network, not the actual network that plays the game. This is because using the network that's playing is far too unstable, so instead we train off of a copy that gets updated every 1,000 frames. And that's it. That's deep Q learning. So to recap, we use a neural network to estimate the reward of each action, either up, down, or do nothing, for each frame, and take the action with the highest estimated reward. We then save to memory the game state, the action we took, the reward, and whether or not it was the last frame. Then, we sample some data from this memory, which we feed into the Bellman equation for more accurate estimate of rewards. Finally, we train our neural network to create estimates that are closer to these new rewards. And now, let the training commence. When the agent is first put into the game, it has no idea what's going on. The reward estimates are just guesses. But slowly, the agent will begin to understand what the game data actually means through training, maximizing rewards. The agent is now playing at a superhuman level, predicting the path of the ball and hitting it with the corner of the paddle for maximum power. Its ability to score on the opponent means that although inconsistent, it takes into account the opponent's position and tries to hit the ball away from it. Deep Q learning is a very powerful tool. Today, I've explained what it is, how it works, and applied it to the game Pong. However, Deep Q learning is a truly general algorithm. Given input data and a reward function, it will attempt to learn any environment, and with enough time and optimization, it'll master a few of them, performing at a superhuman level, even having the ability to teach its creators something new.